Illustrative Math, Algebra 2, Unit 5, Lesson 8 is called Scaling the Outputs. Okay, so what we're going to be talking about today is a vertical stretch or compression. And I actually chose this Bitmoji here for a reason. Because if I have a function here, let's say it's like a parabola type of situation, we are going to be stretching it or compressing it vertically. So it'd be kind of like I took it and I pressed it down. All right, kind of like that. I squished the original from something like that down horizontally, or I could stretch it vertically. So, maybe it was something like this now gets stretched. So that's why I chose the anvil there, because it's kind of, I want you to kind of remember that when we scale the outputs, we're gonna squish our function, squash it down towards the x-axis, or we're gonna stretch it away. All right, so our goal today is I can calculate the scale factor needed to transform the output of a function to model data. So if you want to pause the video and write this stuff down here, this is what's happening. I guess this would be here on a graph. I guess on a graph, this would be in your function, and this would be in a table. All right, so that's what would happen. All right, so let's take a look here at this. So what we have here is we have three functions here. The green one is what we're starting with. The green one's y equals x squared. If I multiply the entire function by a number greater than 1, it's going to stretch away from the x-axis. So the purple is an example where I multiplied that function by a number greater than 1. And what you see here is it gets stretched vertically. Now, if that number that you multiply by is between 0 and 1, then your function gets shrunken down towards the x-axis or compressed. Okay. So here's a picture of an arch. What do you notice? What do you wonder? All right, so I put here, the arch looks like a parabola. It's symmetric about the center. So kind of like if I put like a line right down the middle, right there, that would be symmetric there. Some things that I might wonder here. How tall and wide are the arch? Is there an equation for this arch? If I put on a graph, where would the x and y axis be? Okay, like, would your x axis be right there and your y axis be right here? Or, would, my y axis be over here? Where would they be? Could I make it narrower, wider, taller, etc.? So, could I maybe keep these points the same, stretch it up like that? Maybe what is this vertex here? Another thing that you might notice as well here, I guess I could write this in here. I would say it appears that the vertex is midway between the x-intercepts. Now that's assuming I have the x-axis right here. If this is the x-axis, these points, if I look at them right here, these points to right here, the vertex up top looks like it's halfway. Okay, it looks like this distance. If I were to kind of do just a quick measurement, they look pretty close. All right. So let's see here. We got an arch right here. The ends are 52 meters apart and 25 meters high. Use the description to help you label three coordinates. So I made it a little bit bigger here, so we can write it down here. This looks like 0, 0. If it's 52 meters apart and 25 high, we know this is 25, This is 52. It's on the x-axis, so the y-coordinate is 0. This looks like it's halfway, so the x-coordinate is going to be 52 divided by 2, so this looks like 26. Okay? Han wants to model the shape of the arch with the graph of function, and he chooses this function. So where did he get that? He got these from the x-intercept. So this value gives you the one that's 0. And then the 52 minus x, that gives you this one. Because remember, if you set each factor equal to 0, all right, this one's easy. Obviously, that's an x-intercept. This one, if I add x to both sides, I get 52 equals x. So those are my x-intercepts, which look like, on your graph where it crosses the x-axis. And then the negative, if I were to distribute this out, it would be 52x minus x squared. So that negative x squared as the highest power, that's what gets us the parabola opening downward. So for the second one here, let's make sure it didn't ask us to do anything. Han wants to model the shape of the arch with the graph of the function, and he chooses this. Okay, so that's good. For the x-coordinates of the 3 points, what are the corresponding points on the graph of H? So I guess what I would have to do for this one is I'd have to figure out what H of 0 is. If I plug in 0 here, I get 0. I have to figure out what H of 26 is. So if I plug in 26 to that function, I'm going to get 26 times 26, which is 676. And then if I wanted to find H of 52, I plug that in and I would get 0. So I guess these two here, I'm going to put a green check over them because these check out. 52, 0 is a point, 0, 0 is a point. The problem is this is not the right point because we have 676 and 25. So Han's function is way too tall for us. Right? It's going to go like, almost up here off the graph. If I go here down to there. Okay, something like that. Sorry for my terrible parabola. I can't even look at that. I have to erase it. So what did he do well? Obviously, he got the direction of the parabola. Opening down. Even before that, I would say he got the general shape correct, which is a parabola. And he got the direction of the parabola opening down correct. He also got the x-intercepts correct. But the problem is it's not tall enough, okay? The vertex is not tall enough, okay? So comparing the height of Han's graph with the height of the bridge, how can you change the output? So it basically what we need to do here for 5, let me erase some of this here. Our vertex, the y-coordinate is 25 on the bridge. We want, our y-coordinate is 676. We want to multiply that by some number, call it C, and we want to get it equal to 25. So if I just divide, I'm going to get C equals 25 over 676. So if I put that number in front of Han's function, and just multiply that times x times 52 minus x, that should shrink it down far enough to what we want. So that would be what I would do. All right, so here's another one. Let's kind of review what we did here. Let's take a look here. We know this point 0, 0. We know this point, if this is my function, 35, 0. How do I get 35? I plug in 35 for x, I get a y coordinate of 0. This would be halfway, that would be 17.5. And then we'd have to plug it into this function to get the y coordinate. So this would be 0, which I wrote right here. This would be 0, which I put right there. 17.5, I don't know, I got to plug it in. 17.5 times 35 minus 17.5, which would give me 306.25. Oops. All right, so there we go. Now, if I wanted to move this up or down, like say I want to scale this down here to, I don't know, let's say 200, we would take this y coordinate, we'd say, okay, 306.25. What constant do we multiply everything by to get it down to 200? And then I could just divide by 306.25. And I would get 0.653 approximately. So I would put that in the front. If I wanted to change it, I could change it to 0.653 x times 35 minus x. That would give me my function there. All right. Certain brand of dog food gives the minimum daily amount of food a dog needs depending on its weight. We want to model the relationship between the amount of food and the dog's weight with the function f, where f of w is the amount of food in grams needed by dog weighing w pounds. So this is w and this is f of w. Okay. Use graphing technology to find a linear function to match the data. So what I did was I took all this data here and I went on Desmos and I typed it all in. Okay, so let me delete this. All right, so here's my table. Now, if I want to get a linear function on Desmos, I'm going to use this feature here. I'm going to type in y1 because that's what my table has. And then I'm going to say mx1 plus b. But instead of equals, I use that little squiggly symbol there, the tilde. And that's my line of best fit there. Okay, and it gives me the numbers right there in my function. So it's going to be, okay, let's write it here, f of w. So m would be 4.1, x plus b would be 44.04. Okay, so there's my linear function that's best fit. What aspects of the data does your function model well? What aspects does it not model well? I would say it appears to be somewhat accurate. I would say it kind of looks, if you look at it closely, it kind of looks like it curves a little bit more. More than it looks linear. Okay, so when I say that, and I'll do my best to draw this. It's hard to draw this here. Kind of looks like it's more curved like that. Okay, that's the best I can draw it there. Because if you look right here, the giant gap where there's no real data on our graph. Okay, so I'm going to erase all that. So here's one that looks a little bit more curved. So if I graph this function, it's going to be a function that has that kind of curve shape there to it. But it doesn't really fit the graph very well, so we're going to have to play around with the graphing technology. So what I would do if I was you and I was watching this video, I would pause it. I would go to Desmos. I would type these data points in, and then I would type in right here. Whoops. I would type in these functions here. Oh, I already ruined it. I type in this function. I play around with the number in front to see how I can stretch it and compress it. All right, and I found 20 was the best number. So if you look here, here's my data again, and then you might have to change your window as well because my window is I already got it kind of set here from like 105, -5, 450, -10. But what I did was I played around with this number and I just kept typing in until I got one that fit it best. So my answer here is going to be, I'm going to say f of w equals 20. I'm going to say capital F of w times lowercase f of w. So in other words, f of w equals 20x to the 2/3. So that's my function there. Okay. And obviously that 20, because that's greater than 1, it stretched it up vertically like that. Okay. This point here didn't change because that's that has a y coordinate of 0. But every y coordinate, it's like I multiplied them by 20. All right. Describe in their own words the effect of a scale factor k on the output of a function. So I would say here, excuse me, I would say every y coordinate of the function will be multiplied by k. So if k is greater than 1, the graph will stretch vertically away from the x-axis. If k is between 0 and 1, the graph will compress or shrink or squash or squish, I don't know, squash towards the x-axis. Okay. So our goal today was I can calculate the scale factor needed to transform the output of a function to model data. We did it graphically with using graphing technology, and we did it kind of analytically by taking a look at it and setting up a little algebra equation. So how would you transform this function to meet your data there? So what I want to do is I want to pick a point here. So this is 4, 4. And what I want to do is I want to look here and say, okay, well, whoops, let me change that here. If I look like that, this is my new function. This point here would be like, I don't know, the x coordinate would stay the same. The y coordinate looks like 1.2. I don't know. I'm going to say, okay, 4 times what number gets me down to 1.2? Well, if I divide, I can find my number. And my answer is 0.3 or 3/10. So my new function would be f of x times c. Okay, so basically that's going to be c times f, value of x, but now we found c, so we're going to call it, give it a new name because I don't want to reuse f. I'll call it 0.3 times the absolute value of x. And again, that's an approximate number here. These ones look a little bit more accurate here. This is 6, and then this looks like 2, right? Might be more like 1/3 in all honesty. If I look at those points, 6 times c equals 2 might be better. Might be better to say it's 1/3, but nonetheless, it's just an estimate here. Okay, 1/3 times the absolute value of x if I look at those points, okay? All right, well, that's it for this lesson. Hope you enjoyed it. Thanks for watching, and we'll see you next time.